Welcome! In today's session, we'll explore the problem number 1450, titled Number of Students Doing Homework at a Given Time. This problem focuses on determining how many students are actively working on their homework at a specific query time. We'll break down the problem, analyze potential approaches, and discuss their complexities. Let's dive in. In this problem, we are tasked with determining how many students are actively doing their homework at a specific time, called the query time. You're provided two integer arrays, start time and end time, which represent the start and end times of homework sessions for each student. For example, the ITH student starts their homework at start time, I, and finishes at end time, I. Additionally, you are given the query time, which is a single integer. A student is considered active at query time if their homework session includes that time, meaning start time, I, is less than or equal to query time, and query time is less than or equal to end time, I. The objective is to return the total number of students who are active during query time. Now let's look at an example to understand this better. Suppose start time is 1, 2, 3, and end time is 3, 2, 7, with query time equal to 4. The question asks us to figure out how many students are doing homework when the clock reads 4. We can analyze each student's homework session. Student 1 is active between times 1 and 3, student 2 is active at time 2 only, and student 3 is active from time 3 to 7. Since query time is 4, we see that only student 3 is active at this time. Therefore, the output is 1. Here's a simpler example with just one student. If start time is 4 and end time is also 4, with query time equal to 4, we can see that this student is active exactly at time 4. There's no other student to consider, and the output is simply 1. This example demonstrates that a student can be active for just one specific time if their start time and end time are the same. Finally, let's consider a case with more students. Suppose start time is 1, 1, 1, 1, and end time is 1, 3, 2, 4, with query time equal to 4. Here, we have 4 students, and their homework sessions can be summarized as follows. Student 1 is active from time 1 to 1, student 2 is active from time 1 to 3, student 3 is active from time 1 to 2, and student 4 is active from time 1 to 4. At query time equal to 4, only student 4 is active, so the output is 1. The constraints of the problem ensure that the input sizes are manageable, but we still need to account for edge cases, like when no students are active at query time or when input values are large. These examples help clarify how to approach solving the problem. To solve this problem, we first consider a brute force approach. The intuition here is straightforward. For each student, we simply check if the given query time falls within their homework interval, start time, I, end time, I. This can be achieved by iterating through the arrays and checking the condition start time, I, equals query time equals end time, I. If the condition is true, we increment a counter. The key observation is that the problem boils down to counting how many of these intervals contain the value query time. This approach is very direct and does not require any additional data structures or pre-processing. In terms of complexity, the time complexity is O(n), since we loop through all intervals once, and the space complexity is O(1), as we only use a counter. The main advantage of this method is its simplicity and efficiency, especially given the constraints of the problem. However, it doesn't involve any optimizations, which in this case is unnecessary due to the problem's inherent simplicity. Now, while the brute force approach is already optimal for this problem, we can consider an alternative perspective. One potential optimization could involve sorting the intervals based on start time or end time and then using techniques like binary search or two pointers to quickly narrow down the relevant intervals. This approach might be useful in scenarios where we need to process multiple query times or if the dataset is significantly larger. For instance, pre-processing the data could save computation in such cases. However, for a single query time, as given in this problem, this pre-processing introduces unnecessary overhead. Sorting would take O(n) log n, and searching the intervals would take O log n, making it slower compared to the linear O(n) approach of the brute force method. Additionally, the space complexity could increase to O(n) if sorting is not done in place. While this method has its benefits in specific scenarios, it doesn't offer advantages for the problem at hand, where simplicity and directness are key. After evaluating the options, the chosen strategy is the brute force approach. This decision is based on its simplicity, directness, and efficiency under the given constraints. Sorting or preprocessing would not provide any tangible benefits here, as we are only processing a single query time and the array sizes are relatively small, capped at 10 cubed. The key insight, or aha moment, in this problem was recognizing that it ultimately reduces to a basic interval containment check. There is no need for advanced techniques when the solution is naturally derived from the problem requirements. While alternative methods like sorting or binary search could be theoretically explored, the additional computational cost they introduce makes them impractical for this case. With this in mind, the brute force approach is both time and space optimal. Here's a simple implementation of the solution. Iterate through the start time and end time arrays, check the interval condition for each student, and count how many satisfy it. This implementation is clean, efficient, and perfectly suited for the problem's constraints. The final complexity analysis for the chosen approach confirms its efficiency. The time complexity is O(n), as we iterate through all intervals once. The space complexity is O(1), since we only use a counter variable and do not require any additional data structures. This ensures that the solution is optimal both in terms of speed and memory usage, making it well suited to the problem's requirements. To tackle this problem, we are tasked with determining how many students are actively doing their homework at a specific query time. We are given two arrays, start time and end time, of the same length. Each pair of values, start time, I, and end time, I, represents the time interval during which the ith student is working on their homework. The goal is to count the number of students for whom the query time falls within their homework interval. This means we need to check if query time lies between start time, I, and end time, I, for each student. The simplest approach to solve this problem is to iterate through each student's time interval, check if the condition start time, I, equals query time equals end time, I, holds, and if it does, increment a counter. This is referred to as the brute force approach, and it is straightforward because it directly checks the condition for every student. Now to implement this approach, we start by initializing a variable called count and setting it to 0. This variable will keep track of the number of students whose homework interval includes the query time. Before proceeding, we ensure that the input arrays, start time and end time, are of equal length, as this is a necessary precondition for the algorithm to work correctly. Next, we iterate through the indices of the start time array, which is the same length as end time. For each index I, we check if the condition start time, I, equals query time equals end time, I, is true. If the condition is satisfied, we increment the count variable by 1. After completing the loop, we return the value of count, which gives us the number of students doing homework at the given query time. There are a few key insights to note about this algorithm. First, the condition start time, I, equals query time equals end time, I, is the core logic. It ensures that the query time is within the homework interval for each student, and this direct comparison keeps the approach simple and efficient. In terms of complexity, the algorithm runs in O(n), where n is the number of students, because we iterate through the arrays once. The space complexity is O(1), as we only use a single counter and no additional data structures. Additionally, there are some edge cases to consider. If either start time or end time is empty, the result should naturally be 0, as there are no students to check. If the query time is outside all intervals, the result is also 0. On the other hand, if every interval contains the query time, the result would be the length of the arrays since all students are counted. The data structures used in this solution are minimal. We rely on the input arrays, start time and end time, to represent the intervals during which students are doing their homework. These arrays are sufficient for the task, and no additional data structures, such as lists or maps, are necessary since we only need to track a single counter. Let's look at an example to clarify the process. Suppose the inputs are start time equals 1, 2, 3, end time equals 3, 2, 7, and query time equals 4. We will iterate through these arrays to determine how many students are actively doing their homework at query time 4. To execute the solution, we begin by initializing count to 0. Then, we iterate through the indices of the arrays. At I equals 0, the homework interval is from start time, 0, equals 1 to end time, 0, equals 3. Since the condition 1 equals 4 equals 3 is false, we do not increment the counter. At I equals 1, the interval is from start time, 1 equals 2 to end time, 1 equals 2. Again, the condition 2 equals 4 equals 2 is false, so the counter remains 0. At I equals 2, the interval is from start time, 2 equals 3 to end time, 2 equals 7. This time, the condition 3 equals 4 equals 7 is true, so we increment count to 1. After completing the loop, we return count, which is 1. This means that only one student is doing their homework at query time 4. While the brute force approach is efficient for this problem, optimizations such as pre-processing the intervals could be considered if we needed to handle multiple query times efficiently, for example by using prefix sums or interval trees. The provided solution implements a straightforward approach to solve the problem number of students doing homework at a given time, LeetCode number 1450. The goal is to determine how many students are doing their homework at a specific query time. The function busyStudent takes three inputs: start time, and query time. The start time and end time lists represent the start and end times of each student's homework session, respectively, while query time represents the time we are querying. Here is the step-by-step explanation of the code. 1. Initialization. The variable count is initialized to 0. This variable will keep track of the number of students whose homework session includes the query time. 2. Iterating through the time intervals. The function uses a for loop combined with Python's zip function to iterate over the start time and end time lists simultaneously. Each pair of start and end corresponds to the start and end times of a student's homework session. 3. Checking the condition. For each student, the code checks if query time falls within the range, start, end, inclusive. This is done using the condition start equals query time equals end. If the condition evaluates to true, it means the student is actively doing homework at query time, and the count is increment by 1. 4. Returning the result. After iterating through all students, the total count of students doing homework at query time is returned as the output. ### complexity analysis. Time complexity. The solution has a time complexity of O(n), where n is the number of students. This is because we iterate through the start time and end time lists once. Space complexity. The space complexity is O(1), as we use only a constant amount of extra space. ### edge cases. The code handles several edge cases effectively. If start time and end time are empty, the for loop will not execute, and the function will return 0. If query time is less than all start time or greater than all end time, the function will correctly return 0, as no condition will be satisfied. If all students have the same start time and end time, the function will correctly count all students if query time matches their interval. This solution is efficient, concise, and handles all edge cases appropriately, making it suitable for production use. This is the Java implementation of LeetCode problem number 1450. The logic mirrors the Python solution, where we iterate over the start and end times of each student and count how many students are doing homework at the given query time. Key differences in Java include explicit type declarations for arrays and variables, as well as the use of standard Java syntax for loops and conditionals. The method is implemented within a class-named solution to conform to LeetCode's structure. To solve this problem, we need to count how many students are doing homework at the given query time. In this example, the input specifies 3 students with their respective start and end times, and we want to know how many were active at query time 4. We start by initializing a variable count to 0, which will keep track of the number of students whose homework time includes the query time. Then, we iterate over the start time and end time arrays. For the first student, we check if their start and end times, 1 and 3, include the query time. Since 4 does not fall between 1 and 3, the condition is false, and count remains 0. For the second student, their start and end times are both 2, and again, query time 4 falls outside this range. Lastly, for the third student, who starts at 3 and ends at 7, query time 4 is within this interval, so we increment count to 1. After iterating through all students, the final count is 1, which we return as the output. Now, let's consider a case where the query time falls entirely outside the intervals for all students. Here, the input specifies 3 students, but the query time is 3, which is earlier than all their homework intervals. We start by initializing count to 0 once again. For the first student, we check if their interval, from 4 to 6, includes the query time. The condition 4 equals 3 equals 6 is false, so count remains 0. For the second student, whose interval is from 5 to 7, the condition 5 equals 3 equals 7 is also false. Similarly, the third student's interval, from 6 to 8, does not include 3. Since none of the intervals include the query time, the final count remains 0, and that's the result we return. In this example, we look at a scenario where all students are active at the given query time. The input specifies 3 students, each with n times of 10, and we want to know how many are active at query time 5. Again, we initialize count to 0. For the first student, whose interval is from 1 to 10, the condition 1 equals 5 equals 10 is true, so we increment count to 1. For the second student, whose interval is from 2 to 10, the condition 2 equals 5 equals 10 is also true, so count becomes 2. Lastly, for the third student, whose interval is from 3 to 10, the condition 3 equals 5 equals 10 is true, so we increment count to 3. After iterating through all students, the final count is 3, which reflects that all 3 students were active during the query time. This problem can be summarized by the key observation that the algorithm checks whether the query time falls within each student's interval, defined by their start time and end time. The condition start equals query time equals end ensures that we only count students who are actively doing homework at the specified time. Edge cases to consider include situations where the query time falls outside all intervals, leading to an output of 0, or when all students are active at the query time, resulting in an output equal to the number of students. This approach is efficient and straightforward, as it processes each student's interval in constant time, making it well suited for typical input sizes. When analyzing the time complexity of the given code, we start by noticing that the zip function is used to iterate through the start time and end time lists simultaneously. For each pair of values, the code performs a check to see if the query time falls within the interval defined by the start and end times. This check involves 2 simple comparisons and a logical and operation, all of which are constant time operations, or O1. Now, if the list start time and end time have a length of n, the loop will iterate exactly n times, once for each pair of start and end times. This gives a complexity of O(n) for the loop, as it scales linearly with the input size. Combining this with the constant time range check inside the loop, the total time complexity of the algorithm is O(n) multiplied by O1, which simplifies to O(n). Now, let's break down the time complexity further by looking at the best, average, and worst cases. The best case occurs when all intervals need to be checked, and since the loop always iterates over all n elements, the time complexity remains O(n). Similarly, in the average case, the loop still performs n iterations no matter the input, so the complexity is O(n). Even in the worst case, where all intervals must be processed, the loop does not change its behavior, it still executes exactly n iterations. This consistency means the time complexity is O(n) across all scenarios. For space complexity, the algorithm primarily uses memory for the input list's start time and end time, which occupy O(n) space. However, since these lists are provided as part of the input, they don't count as additional space used by the algorithm. Other than the input storage, the algorithm only uses a single integer variable count and the zip object, both of which require constant space, or O(1). Therefore, the overall space complexity is determined by the auxiliary space, which remains constant. The auxiliary space used by the algorithm is O(1), as it does not allocate any extra memory proportional to the input size, aside from the constant space needed for variables in the zip object. To compare this solution with a naive approach, a less efficient method might involve iterating through a broader range of time values or performing redundant checks. However, this optimized solution avoids those inefficiencies by leveraging the zip function and a direct range comparison, ensuring that it runs in linear time and constant space. Finally, the Big O analysis confirms that the loop's linear behavior dominates the overall complexity. Since each operation inside the loop is O(1), and there's no nested iteration or recursion, the time complexity is mathematically proven to be O(n). Similarly, the algorithm's memory usage does not scale with the input size, apart from the input lists themselves, verifying the O(1) auxiliary space. This combination of linear time and constant space makes the solution both efficient and scalable. When tackling this problem, there are some common mistakes to watch out for. First, it's crucial to handle edge cases correctly. For instance, if the query time happens to match the exact values of start time, I, or end time, I, it should still be considered valid. Overlooking such scenarios can lead to incorrect results. Another frequent issue is incorrect indexing, such as trying to access indices outside the valid range of the start time or end time arrays. Always ensure your loop boundaries align with the array bounds to avoid runtime errors. Additionally, don't assume the arrays are sorted. Many candidates mistakenly believe the intervals are in order, which can lead to overly complex logic or incorrect solutions. Each interval is independent and should be treated as such. Also, be mindful of efficiency. Using nested loops might seem intuitive at first, but it results in an O, n superscript 2, time complexity, which is unnecessary. The problem can be solved in O, n, with a single iteration. Finally, watch for off-by-one errors. The interval condition here is inclusive, meaning query time must satisfy start time, I, equals query time equals end time, I. Misinterpreting this can lead to subtle bugs, so double-check your comparisons. Now, let's discuss some key insights that are particularly useful in an interview setting. First, understanding interval inclusivity versus exclusivity is fundamental. Many problems involving intervals depend on this distinction, so make sure to clarify the conditions with your interviewer if there's any ambiguity. Next, it's a good practice to optimize your approach early. While a brute force solution works for this problem, always consider the scalability of your solution, especially if the input size grows significantly. Testing extreme cases is another essential step. For example, consider scenarios like empty input arrays, single element arrays, or when query time falls completely outside all intervals. These edge cases often reveal bugs or gaps in logic. Additionally, during interviews, it's important to articulate your thought process. Be ready to explain why you might choose a simpler approach, like brute force, for specific constraints, and highlight its limitations compared to more optimized methods. Finally, this problem ties closely to other interval-based problems, such as merging intervals, finding overlapping intervals, or determining covered intervals. Familiarity with related problems like LeetCode 56, 253, 986, and 1288 can help you recognize patterns and adapt your solutions more effectively. Now, let's explore some alternative approaches and their trade-offs. The most straightforward method is the brute force approach using a single loop. Here, you iterate through all the intervals and check if query time lies within each one. It's simple, easy to implement, and works efficiently for smaller inputs, with a time complexity of O, n. Another method involves binary search, which is only applicable if the intervals are sorted by start time. By narrowing the search space to relevant intervals, this approach improves efficiency. However, for unsorted arrays, sorting the data beforehand introduces an O, n log n, overhead, making it less appealing unless sorting is already part of the problem's requirement. Lastly, for scenarios where multiple query time values need to be checked, a prefix sum approach can be a powerful optimization. By pre-processing the data into a prefix sum array, you can achieve constant time lookups for each query. While this method is highly efficient for repeated queries, it does require extra time and space for pre-processing. Ultimately, the best approach depends on the constraints and the specific nature of the input data you're dealing with. Great job! To wrap up, we've summarized the key points and takeaways from today's problem. This was a fantastic example of using simple iteration and condition checking to solve a problem. Remember to practice similar problems to strengthen your problem-solving skills. Thanks for watching, and don't forget to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!